Going on, everyone? It's your friendly math professor here, Nate Allen. Moving on to geometrically defined vectors and some of their applications. Here we go. A few little definitions I wanted to come across first before we get moving with these. And vectors are mainly used in physics, so we're going to just learn the mathematics behind those. And what a vector basically is it has both two parts, a quantity as well as a direction. And that quantity is what we usually call the magnitude, which is basically just the length or the size. And then we also going to have a direction that is typically going to be used to tell us what direction we're going via some angle measurement, which we've learned a lot about, especially with dealing with bearings. So relative to some plane out in space, we're going to be talking about these vectors, and we'll talk about how they're written and what they look like, and then talk about how to use them as well. So for our purposes, we're just going to call these vectors a directional line segment, because that's what it will have, is basically a line, but only a part of it, a segment, because it's going to have a length. And so you may have heard of magnitude before. Typically that's with earthquakes. And remember, the magnitude was the size of the earthquake. So remember, when we're talking about the length of these vectors, these line segments, we're talking about the magnitude, the size of them. The direction will be used by an arrowhead. And again, that resembles what is called a ray from geometry, and will often be times given that by an angle measurement. There's another term that we're going to be seeing quite frequently, and that is called a scalar. And basically, a scalar is just a real number or quantity that we're dealing with, rather than talking about its direction as well of a vector. So temperature, length, even mass, the weight of something, all examples of just what a real number or scalar is. And so it definitely has a size, a magnitude, but no direction like our vectors. So vectors are often used for force in physics, or velocity acceleration, which you'll see a lot more when you guys start getting into calculus. So a few things that we're going to be utilizing quite frequently in this section dealing with vectors is what is called a parallelogram. And hopefully you remember what a parallelogram looks like. And here are a few of the attributes that we're going to be utilizing most frequently with this. So parallelogram, hopefully you remember, starts with two parallel lines, right? And then with that, it has two other parallel lines connecting the ends of these things. And so when we draw those also should be parallel. And so it's kind of like a rectangle, just pushed to the side a little bit, either direction. And so when we deal with these, we're going to be looking at this quadrilateral that has opposite sides that are parallel. And the way that we do that is usually by this or that notation to let you know that each of those pairs are parallel. Then we also know that the opposite sides and opposite angles of the parallelogram are equal. So if I undid the parallel parts and I just did this to let you know that those are the same length, or that, just like a rectangle. Now it's a little bit different than a rectangle, obviously, because a rectangle has four 90-degree angles. This does not. And that's apparent. But one thing I wanted to talk about is, what if I extended this line and this line out? Now, hopefully you remember what this red line right here is called. We went over it very early on in the class. It's called a transversal. So when two parallel lines are cut by a transversal, hopefully you remember that alternate interior angles are congruent. And so you can see that those two angles are congruent. However, I don't normally have that angle. That's not one that we usually have in our parallelogram, because we had to extend that line, and therefore it's not a quadrilateral anymore. But what I wanted to focus on was number to the second part where it says that a parallelogram's adjacent angles are supplementary. So when we're dealing with this parallelogram, you can see that these two alternate interior angles are equal, but hopefully you also notice that this is a straight angle, which means those two angles together add up to 180 degrees, which means if this one, that angle, and this angle here is the same as that angle, then since these two are supplementary, then so are these two angles. And so again, some of these things are pretty obvious, but wanted to kind of show you. Um, Remember, it also mentioned that those opposite angles are congruent or the same in both of our corners of our parallelogram. So the other thing that we need to quickly mention that we will utilize again is the fact that we're dealing with a parallelogram. But remember, this class is called trigonometry. So ultimately, we want to somehow come up with triangles. And so if I was to draw from one opposite angle to the next, you can see I've obviously created a triangle, two triangles actually, but notice they are not right triangles. So that's why this is in this section with the law of sines and law of cosines. Within this whole chapter, we've been dealing with what are called oblique triangles. Now notice if I drew the opposite diagonal, it does appear that something does happen with those two values. And by those, I mean this diagonal gets cut in half by the other, as does this diagonal. Now, one thing you also should mention and see is we talked about that angle there being supplementary to this whole angle. Notice either one you look at, one thing that does not appear that happens is that those angles do not get bisected like the diagonals do. So these are the things that we're going to be discussing and dealing with in more depth. And if I was to just get rid of a few of these pieces, such as this side of my parallelogram, this side, or one of these diagonals, you can see there that if I had these two, which I'm now going to call vectors by making this arrow and this arrow. And if we were talking about this point right here, this vertex, and somebody pushed this box or whatever it might be in either those directions, either the blue direction or the red direction, and somebody put this much force onto it, and then somebody else pushed this way with that much force, and how much force is going to be what is the magnitude, the length of this thing, okay? Then you would imagine that there's a resultant force somewhere in the middle of these. Is it directly in the middle? Not necessarily. Not unless we each put the same amount of force on it. So this purple vector is what is called the resultant vector. And that is a result from those other two forces of the red and the blue vectors. And so the way that we're going to be utilizing these things is we're going to be finding those resultant vectors and their magnitudes, their lengths. And in order to do that, we're going to have to go back to what we originally did, and we're going to have to draw what I originally had was I'm going to take that blue vector and virtually just slide it up that red one along it and draw that one back in. And I could also do the same thing with the red if I just took it and slid it along the blue. And as you can see, we have now created a parallelogram. And more importantly, we have either this triangle or this triangle, which by the way are the same because you can see they have the same three sides, just in different locations. That's what we call congruence. So those are the types of things that we're going to be dealing with these vectors. And we're going to have to utilize all of the stuff that we've learned in the previous 3 sections or videos, which were on the law of sines, along with the ambiguous case, and then the law of cosines. Example 2 adds in another term that we're going to be discussing, and it is called the equilibriant. Now, you guys may recognize that also as a term just a little bit off. Your equilibrium is what helps you to keep your balance. And in order to keep your balance, sometimes when it's something that you're walking on that's not too sturdy, you sometimes have to put your arms out to try to balance. And if one goes down, the other one has to come up. So when we're talking about an equilibriant, we're dealing with a similar situation. So when they use that term equilibriant, you now know and hopefully get that visual picture of what we're dealing with. So let's draw this out and see if we can't find what they ask. It says to find the magnitude or the size, length of the equilibriant of forces of 54 and 42 newtons acting on some point. This time they're labeling it as point A, if the angle between the forces is 98 degrees. So very similar to the one that we just did. And they want us to find the angle between the equilibriant and the 42 Newton force. As well as at the beginning, they ask for the length or magnitude of the equilibriant. So 2 questions within this one. Let's draw it out to see what we're working with first. So I know I got a 98-degree angle between my 2 forces of 54 and 42. So I'm going to start by drawing that 54 Newton force. And then there was a 98-degree angle that I need to then draw. And so when I go to draw this, I will then use the other force. And that was the 42 length. And so it's not quite a 90 degree. I'm going to have to rotate just a little bit and draw that in as 42 newtons. So now I have my force on either side of this 98-degree angle. And so just like we did before, we can draw this parallelogram. And then once I have my parallelogram, I can then find the what we called resultant vector. Now don't forget, if I find this resultant vector, I'm also going to be able to find that other one that they asked us to find called the equilibriant. So the equilibriant would be the thing that is facing the exact opposite direction from that point A, they labeled it, and it would end up being the exact same length. So trying to draw it as best to scale as I can, the cool thing is I know if I find this value, it's the same as that value as far as length goes. Obviously, it is facing the opposite direction. So it would be a negative rather than a positive. All right. So when dealing with this, I'm going to go ahead and label everything else that they gave me. And we drew in. So that was 42. This one up here was 54 newtons. And then remember, we know that the angle that we were given was cut. It was split. But because that's 98, we know that both this angle and this angle are what are called the supplement of that. So I will take 180 degrees and subtract 90 first, which we know that is 90. And then I will subtract the 8 from that to get 82 degrees. So that's the angle that I'm going to be able to use. And hopefully, one more time, you notice that we have a side angle side scenario. And we will then use our law of cosines one more time. So in order to do that, I'll get rid of this so I have some more space. And I will set up that value of x that I was trying to find in my law of cosines, which is opposite that included angle. Filling all that in for you. And please don't forget to use the 82 degrees. One of the most common mistakes is right here, people will use, instead of 82, they will use the angle that was given, 98. So be very, very careful with that when working these out. So now I will go ahead and take what I know and solve for the x by obviously taking the square root of this whole thing. And again, working this out in your calculator, hopefully you will find that the answer is 64 newtons. Now, since this is 64, that means this is also a length of 64. So that was part A. We found the magnitude of that equilibriant. It is a length of 64. Now, oftentimes they're going to call these vectors V, right? And they'll even put the arrow over the top. And if they want the magnitude, the size, which we know length is always positive, negative would tell us the direction. This would be a V here for that resultant vector, and this therefore would be negative V for this one. Okay, so that's why whenever they'll ask for magnitude, it will have the absolute values on it. But they also asked us to find the angle between, careful, the equilibriant and the 42 Newton force. So if I'm going to go and redraw this in a different way, we're talking about the equilibriant and the 42 Newton force. So that was the red color, which was here. And this was our resultant vector. So all we got to do is try to find the angle that they asked us between the equilibriant and the 42 Newton force. And so for us, we're looking at that 42 Newton force, just that, not 98, right? But that angle there. And the cool thing is we already knew that this one was 82 degrees. And because we're trying to find that angle, then we also know, since this angle is known and this length opposite is known, hopefully you recognize what we call that as our good ratio. And therefore we can use the law of sines. So I'm going to go off to the side and I'm going to set up to find an angle. I will use the sine of, I'll call it angle B, over its length opposite it, which would be 54. And that would then be equal to the sine of 82 degrees that we found over 64. And now, since I have my law of sine set up nice and neatly, I will multiply over by the 54 to get what I wanted by itself. Now, I don't quite have it. All of this, when I multiply it out, will be some number. So remember, in order to find the angle, we're going to have to apply the inverse to reverse our input and output and have what we wanted. So once you find that by punching it in your calculator, you should come up with 57 degrees. Now, the problem is a lot of you will put that as your answer. And that is an issue because you can notice, hopefully, that that angle right there is this angle right here. And they asked us to find the angle here. The cool thing is, since we just found this angle right here, we know that this whole thing is supplementary. So we will then take 180 and subtract the 57 off to find the angle that they asked us to find, which was between the equilibriant and that 42 Newton force. So we utilized the fact that we knew enough in this triangle to find that angle. And then since these are on a straight line, straight angle, then we knew that this angle here would be supplementary to this one. So we found angle B, which was 57. We subtract that from 180 to get our final answer of 123 degrees. which looks more appropriate for that obtuse angle. So a lot of things going on, moving parts, but hopefully again, you see why this is included in this chapter. Because we went over law of sines and law of cosines, we actually had to utilize both. And so as I mentioned earlier, be careful to not assume that your resultant vector bisects any of the angles that those two things that we had formed. Okay. And I mentioned to you, I'd mention it later. So here we go. When will that occur? And hopefully you can see there, only when they have the same magnitude. Because then the forces in either direction would be the same. And so the resultant would be right in the middle, bisecting it. So hopefully that makes sense. Because these next couple, and I'm doing two of a similar type, because these are the ones that are a little bit less intuitive. They don't quite flow in the way that we've learned in the past. It does require a little bit more understanding. So, application based, how can we use this stuff, right? Here's a pretty cool one here. We're going to actually find the force required to keep a 2,500-pound car parked on a hill that makes a 12-degree angle with some horizontal, we're going to call it. Okay. Now, 2,500 pounds might seem like a lot, but remember, 1 ton is actually 2,000 pounds. So we're looking at a 1.25 ton car, and it's on a hill. So the first thing I'm going to do is I'm going to draw what it said, right? It said that we have some horizontal line, right? And then what we're dealing with is a 12-degree angle. Now, I know that's not a lot, but because I don't want to have so much cluttered, I'm going to draw it so that I can actually see it pretty decently. So here's my hill, and there's my 12-degree angle. Okay. Now I have some vehicle parked at some point. I'll call this point C for my car. All right. I'm not even going to draw a car as some people like to do. All right. So when you're parked on a hill, obviously it's hard. And even when you put it into park, sometimes it rolls back a little bit. Um, why does it do that? Well, you guys know a little force that's always on Earth and it's constantly working. It's called gravity. And so that 2,500-pound force is always going to be pushed straight down to the core of the Earth. All right. So when we're drawing this out, the very first thing I'm going to draw is what this thing would do as a force. It would be drawn straight down to the core of Earth if there wasn't even a hill. Okay. Now, a lot of people will be wondering, well, what about the hill itself? Well, yeah, there's also going to be a force there. And that's the force of the hill itself onto that car. And that one's going to be perpendicular to that. Okay. So I'm going to draw this little perpendicular in there, and then I'm going to draw the perpendicular to the horizontal there. So we got a lot going on within this. And obviously you can see there's a few triangles going on here, but one in particular that I'm going to draw that is a little bit strange, and that is the one that connects those two forces. Okay. The one that the car is doing to the hill and then straight down to the gravity core of Earth. Right. And obviously, we already had that going on here. So it's as if I'm taking this side right here, this piece, and I'm just sliding it down and drawing it again. So those two things are going to be parallel. And since this right here is perpendicular, then we know alternate interior angles, this also would be perpendicular. Okay. So I'll just draw this so that you know where that came from. All right. So again, a lot going on. Let's try to keep in mind what we're trying to find. All right. Now, don't forget they did give us a force of the car, which is 2,500 pounds. And we said that car is going straight down. So this force right here is going to be that 2,500 pounds. So that's that one in red there. Instead of newtons, now it's in pounds. Okay. We had the 12-degree angle, and that's it. And what did they want us to find? Keep in mind, they asked us to find the force required to keep the car parked. And so to keep that car parked on the hill, we're going to have to, since it's being pushed this way, we're going to have to push it that way with what is called a equilibriant. That's right. So what I'm going to do is I'm going to put this right here as that length right there, which remember, if I just slide it down, straight down to the core of Earth along this red one, guess what that would make? That's right. It would make this right there. So whatever this is, I'll call it X to keep that car parked on the hill. That's the same as this right there, which is kind of nice because I don't know if you guys noticed this, but this is within a big triangle, this triangle right here. And this isn't just any old triangle. This is what is called a right triangle. So even better than our law of sines or law of cosines, now we can just use sine, cosine, tangent, or any of our trig functions. But we need more than what we currently have. We only have right now this magnitude or side length, and we need to find this one in this right triangle. So I need one more angle in here, and I'd be able to use my hypotenuse of this and my adjacent side if I'm using this, or opposite side if I'm using that angle. So somehow I have to use the only other thing they gave me, which was this angle right here. And if you notice, I have another right triangle right here. And in that right triangle, I know one of the angles, which means I know this angle has to be complementary to it. Since this is 90, we know the sum of the triangle is 180. So that takes away 90 degrees. So then we know the other two have to add up to be 90. So 12 plus what would get me to 90? Or 90 minus 12? Well, we know 90 minus 10 is 80. Minus 2 more would be 78 degrees. So since I know that that's 78, I know all the angles of that triangle. And you might be wondering, so what? That's not the triangle that we're trying to solve for. We need the angles of this triangle. And how is that going to relate? Well, check this out. Because we know the sum of a triangle's angles is 180, and we had 90 plus 78 plus 12 gave us that. Well, then what about this straight angle right here? What if I looked at this whole, not the triangle, but just from here to here? Well, I already have two of those three parts, don't I? I have this 90 right here, this 78 right here. So couldn't we find what that, don't we already know what that has to be? That's right. This has to be a 12-degree angle. That's the only way that this would give us 180 degrees. And if that's 12 degrees and this is 90 degrees, then don't we know what this angle is down here? That's right. It would have to be the 78 that we just found. So now we have all the angles of that triangle, and we can now therefore solve for our x that we tried to say would be what kept the car, what that parking brake has to be able to utilize in order for us to keep the 2,500-pound car on that 12-degree angled hill. So what I'm going to do over here is I'm going to use either the 12 or the 78. Just depends if you like sine or cosine better. But most people will use the 12 because it was what was already given up there. But I'm going to go ahead and use the 78 down here because you can see that a little bit better and more clearly. And if I'm going to use that, I want this first. So don't forget, that is going to be my hypotenuse. So I'm going to have to use the cosine of that 78 degrees, which would be equal to x over my hypotenuse, 2,500 pounds. And when doing that, when I multiply over by 2,500, I have then solved for x. It'll be whatever that is multiplied out, which when you give them their answer, remember how many sig figs since they didn't specify? Well, obviously there's only two here. So even if you counted those as 4, which you can't necessarily with those two, the most we can ever give is 2 because that's all they gave us. If it was 12.15 or 12.37 degrees, then we could give them 4. But in this case, we're going to round our answer to 520. And what would be the unit measurement? Well, this one was in pounds. Now, don't forget, we also talked about something early on, and it was called the co-function. And remember, the co-function of cosine was the sine. And if you did the sine of the other angle or the complement of that, you would get the exact same thing. All right. So either one you decided to use, you should get an answer of 520 pounds. That's how much force would be necessary to keep that car from rolling down the hill uncontrollably.